Okay, let's look at another test for determining convergence. Let's suppose we have a series. Let's suppose we have the series 1 over n squared plus 1, the sum as n goes from 1 to infinity. And then we have another one that's n goes from 1 to infinity of 1 over n squared. And these are very similar. The difference is this first one is n squared plus 1. Now, let's further, just for discussion, I'm going to call 1 over n squared plus 1. I'm going to call that a sub n, and b sub n is going to be 1 over n squared. Okay, so we have these two. Now, here's what we can note. Notice that this thing, 1 over n squared plus 1, that's going to be less than 1 over n squared. And that's going to be true for all n, right? Going to be true for all n. So if n equals 1, we've got 1 over 2 is less than 1. So 1/2 is less than 1. But you can see, you can play around with that. The thing is, the reason I know this is less is because it's got a bigger denominator. So you can see that we've got 1 over n squared plus 1. Well, n squared plus 1 is just a little bit bigger than n squared. And it being in the denominator, we get that this one is dividing by a bigger number, so it's smaller. So in every case, every term of this sequence right here, every term for n equals 1, n equals 2, and so forth, you're going to have a sub n is less than b sub n. Okay? Therefore, we could conclude this, that if you look at these two series, this is going to be less than this. Okay? This is going to be true. Now, what if this one converges? What if that one converges? What does that say about this one? Well, if this one converges, this one right here, and this one right here is less, then it must also converge. Okay? And this is the direct comparison. So what my job is to look at, well, what about this series 1 over n squared? Does that converge or not? So let's think about that. We've got 1 over n squared. So my question is, does that converge? Well, yeah, because this is a p series, and this is p is equal to 2, and we know that that would make that a convergent p series. So since this series converges, then our original series must converge. This is the direct comparison test. So what our job is to find a series that's less than, and if that series that's a series that's greater than, if that series that's greater than converges, then so does ours. So let's look at another example. Let's suppose that I've got this one. Let's suppose I've got the series 1 to infinity, and let's suppose this is 1 over 2 to the n plus 5. Now that looks a little bit like a geometric series, except it's got that plus 5 in the bottom. So, but let's suppose we're given this series. We're blessed with this nice series and we're asked, does this converge or not? Here's the way we proceed using the direct comparison test. We look for a series that we know something about. When I say something about, I mean we know if it converges or diverges. Now, in this particular case, I take note of this series, 1 over 2 to the n. Now, this is a convergent geometric series. See? I mean, you may need to rewrite it to see clearly that it's geometric, but this is 1 over 2 to the n. So that's clearly a geometric series. That converges. And not only that, we know that this plus 5 in the bottom makes this one smaller. So here's what we've got. We've got 1 over 2 to the n, okay? Now, since this one converges, this one must also converge because we have this. So here's the deal. Notice that this series is a positive term series. All the terms are positive, and we note that this one is less than this one for all n, right? For n is 1, n is 2, and so forth. So this is true for all n. Therefore, 1 over 2 to the n converges. Therefore, so this one converges. Therefore, this one converges. That's the direct comparison test. So notice what our job was to find a series that we could compare to this one. We wanted something to compare to our original series. Now, it doesn't just work to show convergence, you can also use it to show divergence. So let's consider this series. We've got n goes from 2 to infinity. We'll start at 2 here. 1 over the square root of n minus 1. Okay, so we've been blessed with this series and we're asked, does it converge or not? And we want to use the direct comparison test. Well, one of the things that really leaps out at us here is that this is 1 over the square root of n minus 1. It looks a lot like 1 over the square root of n. So let me see if maybe I can compare these. Maybe I can compare 1 over the square root of n to 1 over the square root of n minus 1. So let's just see if this will help us at all. Now, so the question is, how do these terms compare? I've got 1 over the square root of n minus 1 and 1 over the square root of n. Now, notice that the square root of n minus 1 is less than the square root of n. So that tells me that this is bigger than this. See? So this one is bigger than this one because it's got a smaller denominator. And that's going to be true, you know, for all n, for all n. Okay. Now, that being the case, what do we know about this? What do we know about this series? That's the question. And let's see if that helps us. Now, what we know about this series here is this is a p series with p equal to 1/2. That means it diverges. So we know this series diverges. And also what we know is that this series is bigger. So this series diverges, and yet, and this one is bigger than this one, okay? So our series must also diverge. So notice what we did was we found a series, in this case, we found a series that diverges that's always smaller than the series that we were looking at. Now we kind of, so the thinking is when you look at this one, you're thinking, that looks a little bit like a divergent series. I wonder if I can find a series smaller than that one that that diverges. And if I can, that will show that one diverges. So you can show a P series, you can use a direct comparison test to show divergence or convergence. Now you have to be careful. Let's suppose that you have this series. So we got n equals 1 to infinity, 1 over the square root of n plus 1. Now this is a little different. Now we're still thinking because it's got the square root down there, I bet this one diverges. Now be very careful because we still think, okay, I'm going to compare it to this series. Okay, but here's the deal. We know that this series diverges. Okay, now And here's something else we know. This 1 over the square root of n plus 1, that series, I want to compare it to the 1 over the square root of n. This series is smaller. 1 over the square root of n plus 1 is smaller than 1 over the square root of n. Each term is smaller. Well, the fact that this one diverges tells us nothing about this one because this one is bigger. So you have to be careful when you're working with a direct comparison test. If you want to show a series diverges, find a series that's smaller that diverges. If you want to find a series that if you want to show that a series converges, find a series that's larger that converges. That's the way we proceed with these.